All right. Well, again, thank you everyone for being here today. It's a real pleasure for me to introduce Wenzhen Yuan. I met Wenzhen just earlier this year at ICRA, and we had a really exciting conversation. But of course, I knew about her work for some time. Wenzhen actually did her undergraduate work at Tsinghua University and then her master's and PhD at MIT, where she was instrumental in developing this very remarkable tactile sensor that we know these days as GelSight. And I think we're going to learn some about that here today. She, for a number of years now, has been junior faculty at Carnegie Mellon and has continued to work on challenges in tactile sensing and in helping robots understand the world through touch, something very close to my heart. She's actually in the process, sort of the lengthy process of moving a little closer to us. We'll be joining the faculty at University of Illinois down in Champaign next fall and setting up her lab there. So great sort of transition coming through Chicago. Anyway, so very much looking forward to her talk today. Wenzhen?
Thanks. Always fun. I will use this one. Thanks very much for the introduction, nice introduction, and thanks very much for inviting me here. It's really an exciting opportunities to get familiar with our new neighbors. So today I'm very excited to come here and introduce our work on using high-resolution tactile sensing to interact and understand the physical world. So as many robotics, so we started our work with the same motivation. We want to make robots to perform more intelligently, especially in the real physical world. So especially when we talk about real physical world, it might be some very messy environment as something like here. So you can see that there's lots of stuff, lots of things going on, lots of mess, lots of uncertainties. But like as a human, very intelligent enough, we can deal with an environment like this very well. But the question is that how can we get a robot to be of a same level of intelligence as humans does? So for example, if as a human, if we want to grab something for dinner or for snack today, we may ask the robot, we may just think about like what we want to get, go ahead, grab some piece of fruit. And can we ask the robot to do that? Especially like how can the robot recognize where the fruits are and successfully grasp them and pick the ones we want? So think about one example, is avocado. So when we try to grab an avocado, so we may say that like, we want to have an avocado that is ready to eat tonight or ready to eat in 3 days. So what does that mean? So that means like we want the avocado to have a proper ripeness, that we can touch it, that we can eat them, and it's of not too rotten or not too raw to eat. And as a human, we can quickly touch the avocado and recognize that it has a proper hardness. It's exactly what we want. So the question is that, how can we make the robot to do a similar level of recognition or perception of the physical world? So to answer this question, we probably want to look into like existing technologies in tactile sensing. So this field has been developed, explored for like several decades. And traditionally, when people talk about tactile sensing, the things came to people's mind is that we want to make a sensor to measure the force distributions over space. So for example, this is a typical sensor that is developed by Robotics. So they cover those dark blue areas on the fingertips and palm of this hand, and they measure the distribution of the normal force with a spatial resolution of several millimeters. So for example, if a human is pressing on this fingertip, you can see this is the output from the sensor. It generates like a spatial map of the contact normal force with very large readings in the middle and much smaller reading in the peripheral area, because we know that human's finger is round and with large pressures in the middle. So this kind of sensor is definitely very helpful. So the first thing we may think about is this egg grasping task. So here the robot is asked to grasp this egg with delicate force. So you know that if the force is too large, the robot is going to crash the egg. But with the help of this tactile sensing, the robot can know immediately when the gripper is in contact with the egg, and it can even control the force so that it's not squeezing too hard to crush the egg. So there are some other examples about how robotics understand using tactile sensing in other cases. So other than controlling the grasping force, avoiding crashing the objects, and the tactile sensors can also help robots to recognize the general shape of the objects, so that they know that the robot can know that we are touching a object that is that is as expected, or are we touching the objects as the proper location instead of unexpected location. So the third case here shows material recognition. So those researchers make the robot fingers slide along the surface, and this vibration will generate on the fingertips can generate some special patterns according to the materials. And researchers have been trying to use that to recognize the materials. But according to those examples, you may say that compared to what humans can do, those examples are very limited. They're limited to a very small subset of tasks, and only works well in a very well-defined lab environment. And it turns out the first challenge comes to the community is that the robot doesn't really have enough nice information from the touch sensors with the existing sensors. And in order to have high-level intelligence, have a better understanding of the physical world, firstly, we need to have a good sensor that can give us lots of information about what the robot is touching. So this is why we start our work on developing a new kind of sensor called GelSight. So it's pretty special compared to existing sensors that it can provide information of a very high resolution geometries, as well as force and torque on the tactile surface. So here I show a quick overview about the working principle of the sensor. So the center part of the sensor is a piece of clear elastomer, and it's painted with a thin layer of reflective membrane. So when we make this elastomer in contact with an object, it may deform, including this surface membrane. And the deformation of the membrane will cause some change in the reflections, especially casting the special distribution of the shading. So we can actually put the cameras on the back and to capture the patterns of the shadings. And especially, we can also set up the light in the patterns we want. So everything is a very well-controlled environment. So actually, if we know the surface property of this membrane and we know the light profile, we can use this image to reconstruct the very fine detailed 3D shape of the objects we are touching. And finally, we have all the components, the light, the camera, this sensing elastomer. We put everything together and put in a small box and make a small sensor like this. That is good enough to be put on the robot fingers so that the robot can use the sensor, move around, grasp, and touch different objects and understand what it is touching or grasping. So another thing we have been trying to do is to paint those black markers on the surface of the sensor. So they are just visual markers, and with the same cameras, we can track the displacement of them. Of course, it's only on the plane. But this proved to be very helpful to tell the information about the force and the torque. So for example, here is my lab mate pressing on the sensor and do a little bit of twisting. So on the one hand, we can still use the optical feedback to see the textures, especially like the fingerprint on the fingertips, but also this twisting causing some torque, and then making a very significant pattern of the rotational distributions of those markers on the surface. So specifically, we actually tried to do a bunch of experiments with different contact situations and found that when we have different kind of force, like either it's a normal force or shear force or in-plane torque, those markers field will generate different patterns. And the magnitude of the marker's motion is exactly linear to the magnitude of the force and the torque. So this turns to be very helpful in many manipulation tasks, especially if we want to know if there are some shear force, if there are some torsions on the sensors, and that can help the robots to better interact with the physical environment through some dynamic setting. So here is an overview about how the sensor works. So I'm showing a demo of my lab mates pressing the sensors on objects. Oops, why it stops? On different objects at different locations. So the second window here shows the raw reading from the cameras, where you can see that there's a significant change of the color. So that is caused by the optical change and exactly matches the geometry information of the objects or the surface the sensor is touching. And the third window here, I'm showing the motion of the markers with those like yellow arrows. And the field of the markers exactly shows like the contact force. So in those cases, you can see that it's very typically we will have the four markers moving towards one direction instead of like spreading patterns, although my lab is only intending to press the sensor on the surface. That is because this contact is conducted by a human. And human is always very bad in controlling our motions. So although like the human's intention is only doing the pressing, but it's always inevitably some like shear force and torque is included in the process. But our sensor is very sensitive and can capture all those information together. Okay, so that is a quick overview about how the GelSight sensor is designed and its working principle. So any quick questions so far? Go ahead.
The dots look very hand-drawn. Do they need to be precision placed on the flexible membrane, or?
That's a good point. So the distribution of the dots is not that much important because we are using the field. So as far as we can have the dots distributed over the surface, not neither too dense nor too sparse. So that is good for the function side. So, but you're right. Like, we have like in the early stage, it's lots of human labor involved here. That's probably would explain like why the dot doesn't look so beautiful to you. Good.
So why cannot be too dense?
So actually, we are trying to get two channels of the information together from the same camera's output. So if you have too much dots, you're actually blocking the places we are detecting the geometry using the optical feedback. So that's why like we don't want the dots to be too dense.
Okay. Because I'm thinking about when people do speckle patterns, it's much dense. But maybe we can talk about this later.
Yeah, that's a very good point. Thank you. Okay, go ahead.
What's the sampling rate of the camera?
So that pretty much depends on the camera itself. So our first versions have been using the off-the-shelf USB webcam, so which is very easy to use, but unfortunately the frame rate is pretty low. It's like 30 frames per second. So we have been using this sensor for most of the work I'm talking about today. But like in recent years, we have been exploring like new technologies, new cameras where we can reach a speed of like 90 frames per second. So that makes like especially manipulation tasks or dynamic interactions much easier for the robot. Okay, so now we have the sensor. We may ask questions. This kind of high-resolution tactile information doesn't exist before, but now we have it. How can we use that to help robots? So the first thing that came to our mind is that we can easily recognize the shape and the material with the sensor. So here it shows an example of our previous work about using the tactile sensing to recognize the clothing materials. So here we make the robot go down to grasp the clothes, natural patterns. And you can see that this is what we can get the data we got from the GelSight view. So the textures of different fabrics, different clothes can appear to be very, very clear from the tactile views. So we can use that to recognize like the type of the fabrics, the type of the yarns. But on the other hand, we can also see the overall change of the shape. Like sometimes it's a very thick materials, and sometimes it's much thinner materials. So this information is also embedded there. So we can also use this tactile information to recognize those properties relevant to the clothes. So another examples we have been doing is using high-resolution tactile sensing to help manipulation. So this is also our earlier work on trying to do a USB insertion test. So the robot is commanded to grasp this USB head from this hanging place and move it towards the USB hole and finally finish this plug-in work. And one of the biggest challenges in this task is precision, because you can see that like if you miss the holes for like 1 millimeter, you cannot get your USB head into the hole. But with the help of GelSight sensors, we can recognize these special textures on the side of the USB head, and that can help robots to do a very precise in-hand localization of where exactly is this USB head in the gripper. And the robot will update its manipulation strategies based on this information, and therefore can do a very precise manipulation. So, but then we ask the questions. Those things looks like pretty straightforward as far as we have this nice information. How can we get deeper understanding of the physical world with the high-resolution tactile sensing, especially thinking about like the first example we talked about at the beginning of the talk, this avocado case. As a human, we can easily recognize the hardness of the avocado as soon as we touch it. Can we make a robot to do similar kind of perception? So we started with the toy examples. We try to make this like silicon samples in a dome shape and we press our GelSight sensor on the top. And this is what we see from the output of the GelSight sensor. So you can see that it's a round area, it's growing because of our pressing with a larger force. And the change of the color indicates the shape, the surface normal. So that means like it's a dome shape, so we can detect it's like changing slopes on the contact surface. And we'll also do the same experiment with another sample that is of exactly the same shape but made of material that is much softer. And this is what we see this time. You can see that it's still a round area, it's still expanding, but the color is much dimmer. So why? Because the dome is not as sharp as the first case. And that is because during this press, if the object is soft, it may also deform. And the more deformation the object makes, that means like that there's a much more significant change of the geometry of the object surface on the contact areas. And the good thing with GelSight sensor is that we can exactly measure how much deformation of the geometry it is. And we can try to quantify that and use that as a clue to help us to estimate like what's the hardness level of this material. So it turns out another clue that is very helpful is the force. So when we try to press on the sensors on the objects with of a much softer materials, it's very common for us to use a much larger force. And the force can be easily tracked by measuring the motion of the markers, especially the magnitude of the markers. So here I'm showing comparison about like the motion of the markers when pressing on harder objects and on the softer objects. So you can see that in the first case, the marker has a much larger movement. That is because the normal force is much larger. So finally, we found that this is a general clue. Like, firstly, we can measure how much the geometry changes, and secondly, we can measure like how much the force increases. And we use that can infer the information about the hardness of the objects. So to get a quantitative measurement, we actually use the neural network structures. So get a sequence of GelSight contacts and get a bunch of frame from the contact sequence and feed that into a neural network structure. Firstly, is a convolutional neural network, which detects the spatial information within the frame that indicates like the current geometry of the contacts and current motion of the markers. And then the information flows into a recurrent neural network, which tells about like temporal information. And here the network is actually trying to calculate like how the shape and the contact force it changes according to as the time goes. And finally, the neural network will come up with one number that describes the hardness of the objects. So we test our models with different settings, like either with objects of different hardness levels or different geometries or even different contact mode. And seems that the model is giving us like a reasonable prediction of the hardness levels for all those cases. And of course, we care a lot about the avocado. And here we don't really have a ground truth about how hard the avocado is, but we ask a human for help about putting the avocado from like soft to hard and make a GelSight to touch them and try to predict the hardest numbers out of the contact sequence. And it seems that the prediction of our model exactly matched the human perception. Okay. So that's the part of our work exploring how to detect the physical property of the objects like hardness. And then we look into another direction. We want to find how temporal information can help us. So we're looking into the example of water in a bottle. So as a human, it's pretty common for us to shake a bottle and we can feel the vibration, and that tells us lots of information about the things in the bottle, such as like, is it water or some very sticky liquid, and how much liquid is there in the bottle. So the question is that like, how can we make a robot to do similar things? So there actually have been some existing work about in robotics that people make a robot to shake a bottle, get some special vibration patterns, and try to classify the vibration patterns and recognize the objects. But we want to get a deeper understanding about what is exactly happening there, and how can we make a correlation between those temporal contact patterns with the physical properties of the contents in the bottle. So we start by looking at the simplest case, the simplest shaking, just an impulse stimulus, like a human pressing a bottle, pushing the bottle from one side to the other side, and we wait there and look at the vibration pattern. So you can see that, like in those cases, we compare like a water, oil, detergent, which are who are very, very different in terms of the viscosity. And that will make a big difference in the vibration pattern, like how much vibration it is and how quick they dies out and the frequency of it. So we'll try to see like whether this can help robot with perceptions. So we have been trying to we're doing the same thing with a robot carrying a GelSight sensor. We shake the bottles from one side to the other side, wait there, and collect some tactile data and see what can we get from them. So the most significant signals we see here is the change of the shear force and its temporal change. And we reduce the dimensionalities and get the signals in the pattern like this. It turns out to be very close to a damping signals. So we just feed the model of damping signal to the signal we get. So we finally reduce the dimensionality of the signals into only 2 dimensions. So one is lambda that describes the decay rate of the signal, and the other one is the omega is the frequency of the signals. And it turns out those 2 parameters can generate pretty significant patterns when we try to interact with different kind of liquids. So again, if we look back into the water, oil, detergent examples, and this is the GelSight data we can get after the shaking. This is the pattern we got. So the data turns out to be make a very significant difference regarding to like both the decay rate and the frequencies. So we try to draw those figures into a 2D plot in the axis of decay rate and the frequency, and they make a very clear boundaries, and that can help us to easily make 100% accuracies in classifications for recognizing what kind of liquid it is. And another thing you may notice that the distribution of the data is very interesting. It's not along a blob, but it's along a line. Why this happened? Because we are shaking the bottle of the liquid with different volume, and it turns out that as we go along this major principal axis of the data, so that's actually exactly linear to the volume of the liquids in the bottle. So after we got this data, we try to see that whether we can go further and do a better quantification task about recognizing the liquids. So we started with a more challenging task. So instead of like very distinctly different liquids, we try to shake the bottles of sugar water with different concentration levels. So we made lots of sugar water from 0% to 160%. So they appear actually pretty similar to humans, but their viscosity are different. And the GelSight sensors are good enough to capture the subtle difference between them, and they also make a very significant make a notable difference regarding to like the decay rate and frequency. So we gather all the data and try to fit our data with the Gaussian surface, and this is a result about like how the data distributed. It actually fits very well, and we can use this simple model to very nicely predict the volume of the liquids in the bottles, as well as like concentration level of the sugar in the bottle. Okay, so that's summarize our attempts about like using GelSight sensor to get some observation of the physical properties of the objects. So any questions so far?
Really interesting. So the sensor, at what frequency are you sensing? Is the camera at 60 or 30 hertz?
So for this one, we are actually using a 30 hertz. So we did, at first we thought that it's very low, it's too low. We started with try to use like a sensor with a very, very high frequency. It turns out that even with 30 frames per second, we can get a very good signal.
Okay, and then so if you go back one slide, or the slide where you showed the classification.
Mm-hmm.
This one, yes, thanks. How did you create that? I noticed that there's a pink area at the bottom left there. I'm
Yes.
just kind of curious how you came up with this slicing of the space.
Yeah, it's a SVM. So it turns out SVM is not smart enough to figure out the big general difference. But like we believe that the major thing is that the data is very well clustered, and even using some simple classifiers, we can very easily classify them.
Okay, but so in this case, you're taking the GelSight data, which is you have these vectors at many different points, and then are you compressing it to omega and lambda?
Yes.
And then you're doing this classification.
Yes.
So not straight from the raw data to classification.
Right. We try to like manually reduce the dimensionalities and fitting a damping signal. So it's only two numbers as a feature vector.
Okay. And then when you were squeezing the avocado,
yes.
What was the representation there?
Oh, that is the raw signal. It's a very high dimensional data. So because in this case, like we do need like very fine details about the shape of the objects. So I didn't show this slides, but this shows like example of the data set we collected to train the network and test the network. So we actually experiment with like objects with very, very different shapes and hardness. So there's like lots of degrees of freedom in the object itself. So it turns out to be like on the information level, I think it's more challenging. So that we do need like high dimensional data as the input.
So to classify the avocados as hard or soft, you were using data from all these other shapes too, or just from avocados?
So these are the ones to help us to train the network. So to make sure like our perception models can be generalized to some arbitrary shapes.
Okay, thank you.
And in that network, the input data,
Mm-hmm.
is it essentially all pixels, and the black dots are being treated as pixels, or are you treating them as distinctive, like their XY coordinates as?
Mm-hmm. So for this stage, we try to fit in the raw signal. But since like we have like relatively large enough data set, so and the network itself is pretty deep. So we expect like the network try to like figure out the location of the dots and the motion of dots by itself.
What is the durability of the GelSight sensor itself?
Mm-hmm.
Does it, if you're running it 30, 40 samples, does it change over that period of testing?
Mm-hmm. Mm-hmm. That's a good point. It's also like a big practical challenge we face at the early stage when we do the experiment. So with the material we use in the labs, so the sensor durability is not that much ideal. It's fine for those cases, but if we make the robot to do like grasping where there's lots of shear and potential tear, so the sensors can last for like I think several hundreds or around 1,000 cycles. But in recent years, especially with the help of my PhD advisors, startup companies, they have been actively exploring new materials, and the new prototype of the sensors is much, much more durable.
For the water bottle example, how much do you think it's
Oh,
hard
sorry.
to hear in the back? In the front you can hear, but in the back you can't hear the questions.
For the water bottle example, I noticed they're mostly rectangular bottles, I assume, so the GelSight could be flat. But if the bottle was instead like an orange juice jug or like a round bottle or like some irregular, a different shaped bottle, how much do you think that would generalize?
Mm-hmm. That's a good point. So I would say this from 2 points. So one is that if the shape of the bottle is not very easy to grasp, so it turns out that is really causing some challenge for us. So we believe that if we improve the data processing method, it will fit better. But now we are just using the hack about like using another amount on the bottle, so that making the contact surface to be flat. But regarding to the shape itself, so we actually have some more studies in the work showing that it can generalize to different shapes pretty easily.
Coming to that question, so with the same liquid
You want to ask the question?
I can try to repeat the question.
Yeah. So is that possible that with the same liquid in the bottle, could you just change different types of bottle and tell which one is which? like tell the different the bottles with different shapes?
We do need a little bit data to calibrate the model. So here I'm showing the results with like two other bottles, and the shape of the models were used. So you can see that the shape of the surface is not exactly the same. It's pretty similar. So the way we do it is that with the new shape of the bottles, we collect a very sparse data and use that few data to fit the new shape of this surface, and then try to test that on the new bottle. And turns out it fits pretty nicely.
Cool. Thank you.
Okay, so that's a part of perception. So the other things we have been actively looking into is manipulation. How can we use the feedback from tactile sensing to help robots to understand more about the surrounding environment and how to react to them? So one example is here, like it's actually our recent submissions. We are asking, trying to make a robot to do a relatively complicated cable routing task. So you can see that on this board, there are three kind of different fixtures, like there's a pillar, there's channel, and finally there's insertions. So the robot needs to grasp the cables, go around different fixtures, and finally reach it. But the good thing is that with the help of the GelSight sensors, we can pretty precisely know where is the cable in the grippers and what is the tension on the cable, especially if the cable is hitting some fixtures on different directions. The robot can detect that by measuring the force on the cables. And then we can integrate that with different primitives when interacting with the fixtures and finally achieve this task. So another big directions we have been looking a lot into is robot grasping, which I think is the most common task for robots for many manipulation tasks. So here I'm showing a very typical frameworks for robot to do the grasping. So there are three stages. So firstly, we may want to use a camera to take a look at the entire space, understand where are those objects, what's the location of the objects, and help the robot with planning, like where do you want the robot to go and grasp on the objects. And once the robot knows where to go, where to grasp, it will use this mechanism and the control framework to go ahead, reach the object, close the gripper to grasp them. But the last step comes from the hand or the finger itself. The robot needs to understand whether the grasp is successful or not. Although you have a good plan, but does that help you? Does that make you to successfully got the objects, or something went wrong in the middle and you actually failed the grasp? So our work has to be focused on the last step. We want to use tactile sensing to help the robots to understand whether this grasp is successful or not. Especially we found out that the most common kind of grasping failure is slip. So it may happen when the robot is not grasping the objects with a large enough force, so the object may fail, may drop. And the thing is that whether we can use a tactile feedback to help the robot to recognize those slip patterns in a timely manner, especially considering the objects we may refer to may have very different shapes, weight, and surface properties. How can we get a general way to detect those slip cases? So slip detection actually has been studied a lot in the community for many years. And there are typically two ways to solve this. One is to detect the vibration during these patterns during the slip process. And the other one is trying to measure the force, the normal force, shear force, and try to compare that with the friction coin and try to predict whether it's a safe grasp or not. But the biggest challenge for those existing methods is that it's very hard to generalize using this method. So usually they expect that you have a very good knowledge about what is the surface friction on the surface, or what is exactly the contact surface normal, or the contact is very well controlled. So that can make it very hard to be used for general grasping cases. So we try to look into whether GelSight information, which we have lots of information from a single contact frame, whether that can help us to get more. So we start looking at some objects that are relatively small and has very rich textures, like this doll and tweezer. So this is what we get from the GelSight during this grasp. So you can see that there are two contact areas. Very clearly, it's a small edge and a small dot here that corresponds to the elbows and the horns on the doll. So if we even look closer, the shape may come like this. And also we have the markers. We know that those markers are painted on the surface. So the robot will close grippers, grasp the objects, lift it a little bit, and we may take another look at this frame. And this is what we may see from the sensors after 96 milliseconds. So here you can see that the geometry has moved for several tens of the pixels, but the markers didn't move. So what does this mean? So this actually means that there has been a very small displacement between the object and the surface of the sensor. So that exactly matched the definition of slip. So that means like although it starts with a very small displacement, but likely this displacement will grow very large, and this object will finally slide away from the gripper. So this is a typical clues we can see when the grasp fails and the object slide away. So another kind of slip that happens pretty often is rotational slip. That happens when the robot is trying to grasp something and long objects. So again, we try to take a look at the small views. We can see those textures, and after a little while, there are some significant rotations. So that's another case of the grasp may fail. So then you may ask, what happens if we're trying to grasp some objects with a flat surface and there's no geometry to help us to track things? So it turns out we still have a good indication from the markers. We know that the markers will make these very nice patterns with there are some shear force caused by the gravity. The patterns may change as the shear force changes. Especially this is it's easier to see the difference if we render a color heat map regarding to the marker's displacement over the field. And this time you may find that when the shear force is pretty small, all the markers is moving towards with a similar magnitude. But when the shear force is much larger, the markers in the middle has a much larger displacement distance, but in the peripheral areas they have a smaller distance. So what does this mean? So this is because when the slip happens, it doesn't happen on the entire surface altogether. It happens actually from the peripheral area first. So in other words, it detaches on your soft skin from the boundaries, and finally this detached area grows, and finally happens on the entire surface. But there is a stage where there's a inhomogeneity distribution of the motion of the markers, and we can exactly use that clue to tell the robot if there are lots of tension on the surface, that means slip is likely to happen very soon. So finally, we combine those two clues. So one is geometry detections for objects with lots of geometry, and the other one is marker distribution for objects without not much geometry. And it can work well for general data set, so we can detect slip in 84% of cases. And then we integrate this slip detection mechanism with a closed loop control framework. So we ask the robot to grasp objects firstly with a very small force, but if the slip is detected, we do the regrasp with a larger force. So this mechanism helps the robot to grasp the objects successfully in 89% of the cases. But another thing we found that is challenging in this experiment is that sometimes the rotational slip happens very often, where we want the robot to overcome this big torque at the grasping stage. And that it turns out to be very difficult. We need to use a very large force, which is actually not optimal for robots. And the best solution is that we want to find the location that is closest to the centroid of the robot of the objects, so that we will only need a smaller force to grasp the objects without any slip. So we found that we can do that with GelSight as well. So we can easily measure the rotational torque on the contact surface, and we try to match that with the external observation of the rotation of the objects. It turns out to be pretty precise. And for the objects with a lot of textures and not a very large areas of context, we can also track the contact area instead of the marker's motion, and that can also help us to know that whether the object is rotating. So again, we try to integrate that in a closed-loop control manners. So we ask the robot to try to grasp objects, but if there's a significant torque or rotational slip is detected, the robot will release the objects and move towards along the major axis of the objects based on the direction of the torque, and finally reach somewhere that where there is not too much torque, so that it can easily grasp the object. Okay, so that's the part of manipulation for robots. Any questions so far? Okay, I'll just try to move quicker. I have too many slides here. So those are examples like show like how we can do grasping and detect slip with robots. But of course, we can nowadays it's very popular to do data-driven methods. So we actually collaborated with people from Berkeley and use a purely data-driven method to do this task. It's like we don't consider the physics. We just make the robot grasping many objects and do many trials and train a very deep neural network and try to predict whether the grasping is successful or not. So the biggest complaint we have about this project is that it's such a painful process to collect the data. So we have the data set of like over 9,000 grasping trials. So that literally means like some grad students need to sit in the lab watching the robot grasping object, releasing things for 3 days. And it's definitely not a good job. So the question is that, can we make everyone's life easier so that we can easily collect large-scale data set without like making a grad student sitting in the lab watching the robot to do things for several days? So the big solution is the next solution people think about is definitely simulation. Actually, simulation has been widely used in robotics for like verifying whether a system can work well. And definitely in recent years, they are very commonly used for collecting large robot data set without using a real robot. So it's make the data collection much easier. But the challenge is that there hasn't been any existing nice simulation model for sensors, especially tactile sensors. So we try to look into the questions and try to build a simulation model for GelSight so that we want to save everyone's trouble for collecting data sets with a real robot. So the first, how to build a simulation model. So the first thing came into mind is that we want to look again into like how the GelSight sensor is designed and try to simulate the process. So we know that it's optical sensors. We have these cameras, this light, and contact surface, and also some supporting structures inside. So that why don't we just put all those parts in simulation and simulate them? So actually, the tool we have been using is tools used in computer graphics community called physical-based rendering. In short, the way it works is that we try to track each individual light rays, like see how they depart from the LED lights, hit any surface, and they may get reflected or refracted. And some of the light will be finally goes into the direction of the camera frame and cause a change in the intensity of the 1 pixel in the camera's frame. But after we sample many light rays, it will form an image very similar to the process of a real camera's imaging. So finally, we use this method, and we try to calibrate all the optical components in the sensor, assemble them in the simulation environment, and try to simulate what's the readout of the cameras in different contact cases and with different form factors of the sensor. So it works reasonably. I see here as a comparison between this physical-based rendering method with the real sensors. So you can see that it works well in all the different light setup cases. So, but we do have it is very nice. Like it also like provides a good insight about how the optics works in the sensor, and even gave us some insight about how to design the sensor. So, for example, we have been thinking about a very challenging sensor design cases. Is how to make a tactile sensors for soft robot. So this soft robot, probably you have seen a similar structure like this. So the entire body is deformable, and although there's a big need about like detecting what the sensor, the finger is touching, but it's really challenging to put any electronic part in that, especially optical part, because everything is changing. So that requires like a lot of careful design process, which is traditional done by trial and errors and took lots of time. But now we are using a simulation. So we try to make a basic structure of a camera, the lights using optical fibers to light the surface, but we try to optimize the illumination design in simulation, and until we find the best design, and we then transfer this design to a real sensor, to a real robot, And our preliminary results shows that it works pretty reasonably. So here is we make a gripper out of this soft fingers with sensors and grasping a fake line. So it's not very clear from far away, but the video actually shows that the sensor is able to see the fine details on the surface. But we still have some complaint about this simulator. Is that it works so slow. It's not very practical to help the robot to collect large-scale data set at the same time. So to do this, we've tried to find another technical solution. It's using a data-driven method. Especially, we try to find a lightweighted model called the example-based method. So where we try to learn from only a very small set of data, which we call it the example, and fit a very simple models over the data so that it can run very fast and very easy to calibrate. And here we try to simulate two things. It's not only the geometry from the color, which causing the difference in the color, but also the force and the torque, which is causing the motions of the markers here. So here shows the model we use to simulating the change of the colors. So the sensor, we can consider that as functions that map the geometry, or in other words, to be more specific, it's only the surface normal of the geometries into a color intensity in the RGB channels. Of course, this may be influenced by the contact location as well. So we're just trying to simplify the correlation with the polynomial function as shown here. And so that to simulate the response of the sensor, we just need to get a good model of these simple polynomial functions, or in other words, we need to characterize those parameters in this functions. And we try to do that from a bunch of examples. And by examples, we mean that we collect some some examples of using a sphere contacting the surface of the sensor at different locations. So each image gave us a good information about the matching between the surface normal into the intensity on the specific location of the sensor. So we then use about only 50 examples to calibrate the models. And it turns out it works pretty well. So here I'm showing an example comparison between the sensor, the reading from the real sensor and the simulation results for different shape of the objects. So you can see that they are very similar. And also the speed is works very well. So our first prototype only runs on CPU. We didn't do any optimization so far. But even on a CPU machine, we can reach a speed of 18 frames per second. So it also works pretty well for objects with a fine texture as far as we have a good ground truth about what is exactly the shape. And we also try to generalize the models to other kind of GelSight sensors. So this is a sensor developed by Facebook, where the optics works pretty different ways than the sensor we are using. But we are trying to use the same method to simulating the sensor after collecting a small set of calibration data. And the simulation result, you can see that is pretty reasonable compared to the real sensors reading. So another thing we're trying to do is to simulating the motion of the markers, which is a good reflection of the contact force, especially the shear force and the torque. So traditionally, this is a very complicated models based on the soft contact mechanics of the soft bodies. But we try to find an approximation using a method called linear superposition. So I'm not going to too much details here, but in short, we're trying to approximate the deformation of each pixel in the planar space as a linear combination of the influence of all the other pixels' influence. So finally, this model also works reasonably, and here shows the result about we use our sensors to contact different shape of the objects with either different normal force or a combination of normal force and the shear force. And it can make mean errors of the marker's motion as a scale of 1 to the power of 0.2. Okay, so now we have these simulators. So it's pretty nice, since that is providing a signal very close to the real sensor's reading and can operate very fast. So we try to revisit this question, whether we can use this to help the robot to collect data with a large scale and transfer to the real robot. So we try to revisit this grasping problem and try to use a data-driven method to solve the problem. But this time, instead of collecting the data in a real, with a real robot, we try to make everything in simulation. We build up this environment in simulation, try to make the robot grasping the objects in simulation, collect the GelSight data, and predict like whether the object is grasping successful or not, and use that to train the network. So here shows some examples of the data we collected. So here is another bottles where the robot is a failure cases where the force is not enough. So this is another case where the object is a little bit long, and it's a little bit heavy towards one end, and the rotational slip can happen pretty easily. So it seems that it turns out like since like our simulators works in a pattern that is very, very close to the real sensor and real robot's readings. So it's very easy to transfer to the real robot. So we actually just did a zero-shot transfer. That means like we train the network directly with simulation data and transfer to the real-world robot directly. And here shows the result about like what happens if we try to grasp a bunch of different objects with pretty much different geometries and properties, and we try to compare the result either training simulation, testing simulation, or training simulation transfer to the real robot, or either using a single frame for prediction or a sequential frame for predictions. So finally, it turns out like we can get an average success rate of 86% and 91%. It depends on like whether we're using only one frame as input or a sequence of frame as input. Okay, so that's the end of my talk. As summary, I'm talking about lots of our thought about how we can use high-resolution tactile sensing to help robots for different tasks. So we start with like introducing the working principle of GelSight sensor, which provides very nice signals about high-resolution geometry as well as like the contact force and the torque. So on the perception side, it can easily help robots to recognize what's the objects, what's the texture, but also it can help robots to estimate some physical property, such as hardness or the liquid with viscosity and volumes from the damping signal. And on the manipulation side, I showed the example about how we can use the GelSight feedback to do in-hand localizations and precise manipulation and secure grasp by effectively detecting translational and rotational slip. And at last, I'm talking about our efforts to simulating the GelSight signals, either using a data-driven method for like easily collect large-scale data set, or using a physical-based methods, which is built exactly based on the optics of the sensor. Okay, at last, I would like to thank all my collaborators and funding support on those projects, and thank you for listening.
I think we have a few minutes for questions, and I guess he has the microphone.
So for your simulation, when you import those different objects in your simulation environment, did you consider their hardness, or are they just rigid bodies?
Yeah, so we're assuming it's rigid body, but another point here is that we're currently only focused on the sensor simulation. So in other words, like we are expecting the robot simulation engine give us a good information about like what is the contact case, and our output is like within the, if we know the contact situation, what is the reading from the sensor. So in other words, if the robot engine or the simulators can know like what's exactly the contact case when contacting a softer objects, our simulator can do the work. But definitely the first step is a big challenge.
Okay, so to my knowledge, the engine also requires the input, for example, like the friction or restitution.
Yes.
How did you extract those information for the different objects that you choose to use?
That's a good question. So for this one, so to make sure like this dynamic process works well, like match the real robot and the simulation cases, it has been lots of challenge. And one big challenge is definitely the friction. So we don't have very good systematic solution for that so far, but for this particular task, we try to use the data to calibrate the friction. So we try to do a bunch of grasping experiment and search a space of different friction settings and find the one that can match match the best with the real grasping results with the real robot.
I have a question about both manipulation and perception, and it can kind of go in two different directions. So if you have, instead of one GelSight on a gripper or a hand, if you had two GelSights, would that get you any additional information if at the same time you made each GelSight smaller so you had to process fewer pixels? I guess I'm wondering about information gain versus bandwidth consumed by the information that you're transmitting.
Yeah, that's a good point. I think it really depends on what task you want and what kind of information is needed. So throughout my work, I'm mostly showing that, like theoretically, with one sensor or with one contact mode, what kind of information you can get and how is that connected to like the perception results or the way you can use the information you can use for manipulation. So of course, like for some more complicated tasks, like you have manipulations or grasping a cluttered environment, having more sensor will be helpful. But like I imagine it's like mostly on the more complicated modeling and combining those information from single sensors, integrate that into a complicated system.
Thank you.
Hi, thanks for a great talk. So I was watching on Zoom and I may have missed some of the early questions. But I don't know if anyone asked whether you've tried to somehow invert these networks, or invert is the wrong word, but to assess these networks for what information is being used to provide these results. It's such a broad set of applications. It's wonderful.
That's a very good point. So we did like some small look into that. It's not very extensively. It turns out for this task, the marker's motion is something like the network cares a lot. We also have some other works for example, this one. So this is actually the entire paper. I'm just showing a little bit of them. But like in this paper, we actually try to feed in this tactile data into a neural network and try to predict a bunch of properties as the output of the system. And we also look into this network. It turns out for this part, like the texture or the patterns of local patterns of those optical responses is the most important to help the network to predict this. So this is, again, I think it's pretty much task-based. So based on the data set and the output we want to get from the data set, the network learn to like grab the information they think is the most important to them.
Is that a question you're interested in? I mean, could you take away information and see if it could still perform the categorization, or?
Yeah, that is a good point. I haven't thought a lot about it, but it's definitely a very valuable direction to look into.
Thanks again. Just a really wonderful talk, and I'm so struck by all of the extensive capabilities of the GelSight. How much information you get, really, with a combination of the visual elements and the deformation of the markers. And it seems like a lot of information, right?
Yes, exactly.
And so when I think about competitive technologies, one thing such as Tactile comes to mind, right? Which is really based just on marker deformations. And I wonder if you could say a little bit about sort of pros and cons, and maybe building on Mitra's question, sort of what's really the most key information, and could you visualize sort of a path forward that reduces the sort of the bandwidth requirements while maintaining some of the remarkable capabilities?
That's a very good question. Actually, I don't think I'm ready to give an answer now, because I think it's a long-term research question. It's what is the really signals we need? So I've been working with GelSight for many years, and my understanding is that we are spoiled. We are so happy to have all those information. So it's always nice. It's always very easy to downsample the information, reduce the information from a very nice source, then like get the high dimensional information from low dimensional input. So, but it turns out like in some cases we do need like a lot of resolution, like recognizing the fabrics and also estimating the hardness. But in some cases, for example, like the shaking the bottles, I showed that like we don't really need that much information. Just the overall motion of the markers, overall change of the force is kind of enough. So my personal guess is that firstly, it really depends on what task we want to do. Secondly, we don't really need a resolution like this. This one has a resolution of like 25 micron. I don't think like that is really necessary. But to give an exact answer about like what is like where is the boundary, so I don't think that is an easy way to do it. So I do have lots of thoughts about like probably we can find this in simulation, because simulation is a good places we can tune the parameters, experiment like with the same data set. Can we downsample this information? Can we upsample the information, adding noise, reduce the noise, so and see what the performance is like. And I think that will give us some insight about like exactly what's the better understanding towards the boundary of the information we need.
Thank you. Thank you. And I'm noticing that we're several minutes over, so we should probably thank you. Really terrific talk. Thank you.